So last time we were talking about shear fronts. We were talking about fronts in general, and we talked about plume fronts and tidal mixing fronts. And we stopped when we were talking about shear fronts. And you remember, these shear fronts are caused by the differential advection of the density field by the tidal current, in such a way that the density field will be strained like that by the laterally sheared tidal current. And that the lateral shears usually are produced by lateral bathymetric variations, and in such a way that these lateral shears will be aligned with the bathymetry. So these would be our long estuary fronts, in contrast to the tidal intrusion fronts or the plume fronts, which are perpendicular usually to the bathymetry. The plume fronts and tidal intrusion fronts are sort of independent of the bathymetry, but these shear fronts are typically aligned with the bathymetry along the estuary. And we mentioned that, they arise from this lateral shear interacting with the longitudinal density gradient, and that there is a reasonable explanation for how these fronts are formed during the flood stages of the tidal cycle, in such a way that by the end of flood you end up, if we're looking here into the estuary with distance and depth, we're looking into the estuary. By the end of flood you have low salinity here on the shallow parts of the estuary, because the currents are weaker there. There's less advection of salinity, so there's relatively lower salinity relative to the channel, where the tidal currents are stronger and there's more advection of salinity coming from the ocean. So you have a lateral density gradient that in turn is a lateral pressure gradient. So you can think of how will the surface elevation look in this situation. It'll tilt down from here to here and then up from the middle there. So that pressure gradient is the one that drives this convergence at the surface and then divergence underneath. So again, this was first proposed by Nunes and Simpson back in '85, 20 years ago, more than 20 years ago. And again, they use this to explain what they call axial fronts, A-X-I-A-L, axial fronts, aligned with the bathymetry. And they said that they observed it. They said in that paper that they observed them in the middle of the channel. And they attributed this mechanism to the formation. And after that, lots of papers used that mechanism to explain the front formation during the flood phases of the tide. Now, as we will see in a minute, these fronts don't necessarily form in the middle of the channel. They can form over the edges of the channel also. So that adds a little complication to them. So this is not the full story. And why isn't the full story? Because if we use the same reasoning during ebb periods, during ebb phases of the tide, if we have differential advection of the density field during ebb phases of the tide, then by the end of ebb, you'll have lower salinity water here, because the tidal currents are stronger. You have advection of lower salinity water in the channel relative to the shoals, where the currents are weaker. So there's less advection of salinity, so the salinity will be relatively higher. That is using the same arguments that we've used for the flood periods. So during ebb tides, you'd have a divergence at the surface. So by this mechanism, you wouldn't have front formation during ebb tides, because you'd have divergence at the surface. However, there have been studies after the mid-'80s, that have shown that you do have fronts during ebb also, and not necessarily in the middle of the channel. They can form over the shoals. And here's an example. This is in the lower Chesapeake Bay. This is for two different experiments. So we have the bathymetry here. This is depth versus distance. So these panels down here are in different orientation than these upper panels. So again, this is the bathymetry. We're looking into the estuary, so you have this channel, a shallow part, and then another channel here. And what we see here contoured is the surface flows. You see the arrows? I don't know if you can see the arrows. but the arrows pointing downward in this figure represent ebb, and the arrows pointing upward represent flood. So we have distance versus time. I think you've gotten used to these representations by now of distance versus time of a property. So we have the vectors here, and the contours of what you see here is dv dy, which is a proxy for convergence. So in regions of strong convergence, where dv dy is negative, you'll have front formation. You'll tend to have front formation. And what is something that strikes you, say, from this panel here? The negative values are regions of convergence. The dark blue areas are regions of strong convergence, so you can see here. And they're associated with the edge of this channel. So during this phase of the tidal cycle, you have strong convergence over this edge of the channel, and then during flood, you have convergence over this other edge. But notice the alternation is it's remarkable. Only in this channel. Not in this channel, because this is where the plume outflow comes out in the Chesapeake Bay. So the plume doesn't feel the bottom, so you don't have the bathymetric effects on the convergence, on causing convergences or divergences. But here the flow is closely linked to the bathymetry, and this channel allows the currents to be stronger in the channel, and at the edge of the channel you have strong convergences. Notice that over this edge of the channel we have the convergence during what phase of the tidal cycle would you say? That's right, that's ebb. And why do you say it's ebb? Because the arrows are pointing downward, right? So we said that was ebb. So notice how nicely every ebb we have this strong convergence aligned with this area. And then every flood we have this strong convergence on the other side. So this mechanism that I showed you before in the previous slide of convergence in the middle of the channel does not hold anymore. There seems to be that there is another mechanism that can form these fronts also. And it's areas of strong lateral shear associated with sharp changes in bathymetry or with changes in bathymetry. So that was one experiment that was in, I think it was, I don't remember, I don't have the dates here. Oh yes, right here, end of April of 97. And then here you have end of July of 97. So again, you see these alternations of convergence with every ebb on this side of the channel. You don't have the flood convergences because the channel didn't get as far, so you don't see these convergences during flood. So we also observed this in the James River, but I'm not going to show you the data. The data show essentially the same that I showed you. So we have proposed the following mechanism that can produce these shear fronts, these along estuary fronts. And you don't need a density gradient for this mechanism to hold. That is, we are arguing through this mechanism that you don't need lateral density gradients to cause convergences and fronts. What you need is just a sharp change in bathymetry in such a way that this is by the end of flood, or near the end of flood rather, the flow is still going into the estuary in the channel, but over the shoal it's already turning toward ebb. And the way tidal currents should turn under a homogeneous situation is counterclockwise in the northern hemisphere. That's consistent with a Kelvin wave or with any theoretical tide. You remember Kelvin waves? So they tend to rotate in counterclockwise fashion. So if the tidal current is rotating in a counterclockwise fashion, and there's a phase advance over the shoals, then over the shoals the current is going in that direction, so there's effectively a divergence over this side of the channel. And then here, over this relatively short shoal, the flow is going already turning, so there's a strong convergence in this area. So that's at the end of flood, you get the convergence on the right-hand side, right slope of the channel, as if looking into the estuary. And during ebb, again, the tidal current is rotating counterclockwise. Toward the end of ebb, the flow is still going out of the estuary in the channel, and it's starting to turn over the shoal. So it's starting to turn in a counterclockwise fashion. So that's going toward the channel, and this away from the channel. So you have a divergence on the right-hand side of the slope, on the right-hand slope of the channel, and then you have a convergence on the left-hand slope of the channel when you're looking into the estuary. So this is a mechanism that can explain the alternation of the fronts during ebb and flood, but also you can use the effects of the Earth's rotation to explain this. How is that? Well, what happens is that you're going to have to imagine this a little bit. The same situation here toward the end of flood, the current is still going in the channel and it's starting to coming out over the shoal. So because of rotation, this arrow will be deflected to the right, the inflow will be deflected to the right, and the outflow will be deflected to the right also. So you'll have a convergence here, and here, since it's coming out and deflected to the right, it's going to go away from the channel, and here on this edge of the channel, also away from the channel. So you have a divergence over this slope and a convergence over this slope. When you use Coriolis to explain these convergences. But before that, let me go back and ask you, does it make sense that by the end of flood, the flow is still going in the channel and starting to go out over the shoal? I didn't ask you if that makes sense. Why would that be? Why did I write there that there's a phase advance? Do you remember? How is the tidal current different in the channel relative to the shoal? Is it stronger or weaker? Stronger. So if it's stronger in the channel than over the shoal, what's going to happen when the tide tells the flow, hey, it's time to come back, time to turn around? The bicycle effect. So over the shoal, it's going to turn earlier, right? So that's why we're seeing this different. So again, you can use the same phase difference between the channel and the shoal to use the Coriolis, the Earth's rotation argument, to explain convergence on this side, divergence on this side by the end of flood. And then toward the end of ebb, again, the flow will be deflected to the right here, and as it's trying to go in over the shoal, it's going to be deflected to the right, so you're going to create a convergence on this side over this left-hand slope. And then here, as it's deflected to the right, it's going to go away toward the middle of the channel. And here, as it's trying to go in, it's going to be deflected away from the channel, so you'll have a divergence here during ebb. Does that make sense? So again, we still need a careful study, and probably the best way of doing this is numerically with a numerical model to reconcile all these ideas: the convergence front in the middle of the channel versus this phase advance that we see in this cartoon versus the effects of the Earth's rotation. So those are three ideas that are complementary, but at the same time they're somewhat different. So we need to come up with a coherent picture of what dominates when. Actually, the bathymetry, the shape of the bathymetry will be an important aspect, but also whether the effects of rotation are important or not. So there's a big question that you can explore with some of your data too. And this mechanism of differential advection. Now, if we add density to this field, you have differential advection of the density field. That mechanism of differential advection of the density field by the laterally sheared tidal flow has been used in this paper by Lec14a and Geyer in 2004 to propose that the nonlinear term in the momentum equation, the VdU dy, the term associated with the lateral shear, will cause an order 1 dynamical effect on the estuary. So, in other words, the framework of pressure gradient balanced by friction will be altered. We will need to include the effects from the lateral shear in the flow. How is that? Somebody's going to look into that, right? For your project. So you're going to use the data from Panama City, right? Or from Ponce de Leon? Ponce de Leon. Is there anybody from Panama City going to look at that? Maybe no. Well, that's something that's relatively straightforward to look for. That is looking at the term V du dy throughout the tidal cycle and then average it and see what happens. See whether the spatial distribution of that term looks like the mean flow. So what we have here, these are numerical simulations. Notice the bathymetry is relatively straightforward. And we have the mean flow here. We're looking into the estuary. This white area of the unshaded contours represents flow out of the estuary, so flow going toward you. And then the shaded area is flow going away from you into the estuary. So that's the estuary in circulation. But now notice the lateral circulation. The lateral circulation shows this convergence in the middle of the channel and then divergence. And this arises from the fact that during flood you're going to have this type of lateral circulation. But by the end of flood you're going to have a very strong lateral circulation because of differential advection, allegedly. That is where we saw the mechanism, right, that generates this. So you can imagine that this is the picture by the end of flood. So when you average out over the tidal cycle, the lateral circulation in the other phases of the tidal cycle will be very weak, in such a way that when you average, this persists. So that's the mean lateral circulation. So this mean lateral circulation, think of the term V du dy. So V, which is the lateral circulation, will redistribute the U in such a way that there's a feedback between V and the lateral shear in the along estuary flow that redistributes the momentum. And this distribution is a distribution of those terms, the term V du dy, averaged over the tidal cycle, plus W du dz. Remember that W du dz can be obtained from a numerical model. It's much more difficult to obtain a W du dz from observations because we know very little about the W's, the vertical velocities. Unless you have a very strong and coherent signal, you can measure the W's, the vertical velocity, with a moving platform. Otherwise, you get a lot of noise because the platform itself is moving vertically. Right? So to determine that W du dz is difficult observationally, but a numerical model gives it to you straightforward, in a straightforward way. So again, this representation is for those two terms, the V du dy plus W du dz. What term are we missing here for the advective terms in the momentum equation? There's one term that's missing, and that's u du dx. So why do you think it's not included here? What would be the justification to neglect it? If there's no du dx, if there's no changes of the along estuary flow in the x direction, how would that happen? If you have that this channel doesn't change along the estuary, if the bathymetry doesn't change along the estuary, then there's very little reason to believe that the U flow will change along the estuary. Does that make sense? So that's why it's not included here. But in a realistic situation of changing bathymetry along the estuary, that probably should be included too. The point here is that nonlinear term has a shape, if you see, of the mean flow. So this is contributing to reinforcing the outflow, and this is contributing to reinforcing the inflow, which is the effect of the of the pressure gradient, the combined slope and baroclinic pressure gradient. Right, the slope will tend to push the water out of the estuary in the entire cross section, right? Because light water in this representation we're looking into the estuary. Our river will be far away into the screen here. And the water will be higher. The water elevation, the surface elevation will be higher up there in the river than where we are looking. So that slope in the surface elevation will drive water out of the estuary in the entire cross-section. What causes this inflow? This inflow. For the case of a pressure gradient, what would cause an inflow? Why don't we have just water going out? The baroclinic pressure gradient, right? The baroclinic pressure gradient, and remember that increases with depth, so it's strongest at the bottom. So that's the one that drives the water in. So reinforcing that pressure gradient is this advection term. They call it here time average lateral advection. And I don't know why they call it lateral advection. Do you know? Because it has DUDZ, WDUDZ. It has vertical shear also. Do you know why they call it lateral advection? Ben? No? Can't hear you.
It's produced by lateral circulation.
Because it's produced by lateral circulation. So again, these lateral circulation redistributes momentum, and that's why they call it lateral advection. But anyway, again, the point is that we're talking about shear fronts, and these shear fronts will tend to drive a lateral circulation that sort of looks like that by the end of flood. And also by the end of the tidal cycle, if we average, that lateral circulation will look something like that. And that lateral circulation will redistribute momentum in such a way that the nonlinear terms will have the same shape as the net exchange flow. So the bottom line here is that tidal advection, differential tidal advection mechanism can cause an order 1 influence in the dynamics of the estuary. Okay, this is for weakly stratified conditions. For strongly stratified conditions, this would be the mean flow. And again, these are numerical simulations. So notice the difference. The maximum outflow here is 15 centimeters per second versus 10 centimeters per second maximum inflow. When you have a strong river discharge for this particular geometry, you have the outflow close to 40 centimeters per second and the inflow also close to 40 centimeters per second. In that case, notice that the shape is vaguely similar, but not as in this case, and the lateral circulation is much weaker. So the lateral circulation is much weaker, so it has less influence of the dynamics. So this term, the lateral advection term, or the VDUDY, will depend on the stratification. Now we don't know how yet, because we only have this numerical simulation. We don't have observations to show how and how the bathymetry might change the influence. So another hot topic. All right. So we made a connection now between fronts and the dynamics of the estuary. So we're going to